So hello students, I am really happy to teach this particular technique. This is very important and more effective technique in work power energy. So first we will try to understand what is a question as given, then we will solve the problem. So we are light spring of constant, so the constant value is given and natural length of the spring is also given, that is fixed at a point O. So we assume that this is a point O and this is fixed here, and mass of 1 kg attached to the other end of the spring, and the sleeve start from rest. So it start from rest and it's moving to, like, what will happen if it is a smooth vertical circular wire. So it started sliding down and it is coming here, like a second diagram is given, like here you can see that. And now when it is reached point B, what they are asking is that what is a normal force. So the radius of the circle is given. So we know that what is a normal force at a point B. So you know that in vertical circular motion, the normal force is not same at every point. The normal force is actually slightly trickier one. You have to go and visit that again, like revisit that. But we know that normal force actually point B is mv square by r. So which means that we have to find out what is the mass velocity divided by r. So that is a first thing. Second thing is that how to do this. So of course here work power energy is involved. So we are going to use a more effective technique is that using conservation of mechanical energy. So conservation of mechanical energy is only applicable for conserved forces. Here no non-conservative forces like friction. If there is a friction, you cannot use conservation of mechanical energy, but you can use the work kinetic energy theorem, that you can use, but you cannot use this theorem, like this energy. So here what is conservation of mechanical energy? The total mechanical energy at the point A is equal to total mechanical energy at the point B. So initially they are rest, which means that at the point A, so the kinetic energy is actually 0. At point A, kinetic energy is 0 initially, okay. And the potential energy, there are two types of potential energies are involved. One is gravitational potential energy, because it's a vertically height. So because it's a vertical circular, right? So O point is different level, B point is different level, A point is different level. So to understand this gravitational potential energy, the reference point is very important. We'll take that reference point as a C. C is a reference point. If C is a reference point, so what is the height of A? R, right? So the gravitational potential energy, so the potential energy there is summation of both. One is a gravitational potential energy, one is mgr. So mgh instead of that r, because r is a here height from the C, the center point. And same way there is other potential energy that is involved, because already spring is actually that is expanded. So they gave, what they gave is that they gave that it is actually root 2r is a natural length. So natural length, and how much it got expanded here from the diagram you can understand that. So the expansion is 2r. So now you see that to find out that the expansion is actually, what I'm saying is that, so you see that in OA point, okay, so it's 2r. So it's like a final expansion, like final we can say that length. So natural length is root 2. So I want to find out expansion. So how can I find out the expansion? So that is 1 by 2 k expansion square. So what is expansion? That is a final position or final distance, that is 2r minus what is natural length? That is root 2 r whole square. Root 2 r whole square. You understood? So I want to find out expansion. So what is my expansion? So it's already expanded from the natural length. So natural length is root 2r. So expanded to 2r. So that is, if I take the difference, I'll get the expansion. So this is a gravitational and as well as a spring potential energy that is stored here. In same way, we can write for point C. So of course what we can expect is that at point C kinetic energy is non-zero, because there is some motion here. So the velocity is v, so mass is m. So what I want to find out is that normal force. We already know that what is normal force, mv square by r. But don't forget that here the kinetic energy I am writing here at point B, the kinetic energy is actually, final kinetic energy is 1 by 2 mv square. What about the potential energy? This is final potential energy. Again, it's here there will be two potential energy. One is a gravitational potential energy and it is spring. So you can see that the gravitational potential, I took previously C as a center, like origin, right? So it's in same level. So what is the height here? 0. If height is 0, the gravitational potential energy is 0. Point number 1. Point number 2 is expansion, like gravitational potential energy. Other one is spring potential energy, that is 1 by 2 k expansion square. So what is actually, you see that this is r and this is r, this distance is actually root 2 into r. So what is a position, or else what is the final expansion, final length of the spring is 2r. What is the natural length? Is again this is root 2r. So again natural length is root 2r. So which means that is in natural length. So which means that root 2r minus root 2r. So don't forget what is root 2r. This is my final length of the spring, and this is natural length. Both are same. So if I am squaring it, again what I will have is at 0. So now you just see that the potential energy is 0, okay, and kinetic energy is 1 by 2 mv square, and here kinetic energy is 0 and potential energy this value. So this is, let's say, equation number 1, and this is, let's say, equation number 2. So I can equate both. Total mechanical energy means a kinetic energy plus initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. So my initial kinetic energy is 0. I don't want to mention that, but initial potential energy is simply mgr plus 1 by 2 k, okay, 2r minus root 2r whole square, okay. So this is one thing, and that is equal to other side final kinetic energy is 1 by 2 mv square, and I don't want this other term 0 to mention here. And now what we can do is that, so equation is set, and what is the common thing? 2 is there. Other thing is that we can introduce what is a k value. Don't forget what is the k value is given. So k value is actually 2 plus root 2. So they gave with the proper idea to simplify the results easily. So now I'll take LCM because I don't want 2 here. So I'll remove the 2. So how can I write that? 2 mgr, okay, plus instead of k I'll put that k value as something like this. So what is the k value? So 2 plus root 2 is a k value, and when I subtract this, you just see that this is 2 minus r the whole square. So what I can do is that I can take r as outside. If I take r outside, so this will be rewritten as something like this, 2 minus root 2 of square, okay, into r square. So I'll write it as this is as r square is equal to mb square. So there is a r term here. I can take here one r that side. So this will be mb square by r is equal to mv square by r is equal to, so 2mg plus, so 2 plus root 2 into 2 minus root 2 into r. So don't forget that what is mv square by r? This is my normal force, okay, this is my normal force. If I solve that, what are all the mass values? I'll substitute all the values. So here 2 into mass is actually 1 kg, so 1 into g value will take approximately 10, so this is 20, okay. So plus, so you know how to simplify this. So how can I simplify this? I can rewrite this as something like 4 minus 2 root 2. So I'll write like this. So there is a square term here, don't forget that. And now what is r value? 5. So now this is 20 plus, here again 20 minus 10 root 2. So approximately this is 20, and 10 root 2 is, I can write it as something 14.1, approximately take it as 14. So 20 minus 14, 6. So it will be 26 Newton. This is my normal force, 26 Newton. Okay, thank you.